This video is about light-emitting diodes. It corresponds to section 22.2 of the Applied Analog Electronics textbook. Now, just as a reminder, the symbol that we use for a light-emitting diode is a diode symbol, but with an arrow added to it, sometimes a wavy arrow, to indicate that light is being emitted. Now, the way light-emitting diodes work requires quantum mechanics to really understand, but basically what happens is when an electron and a hole meet, the electron falls into the hole and releases energy, and the energy it releases is the amount of the band gap of the semiconductor. And that means that the wavelength of light that you get is moderately well controlled. It's not as precise as you would get, say, from a laser diode, but it is within a reasonably narrow range. So you can think of LEDs as being almost monochromatic. Okay, the amount of light we get is basically proportional to the number of photons we get. It is the number of photons we get. And that's proportional to the number of electrons that fall into holes in the active region of the LED. The ratio there is actually referred to as the internal quantum efficiency of the LED. And it turns out that that's actually fairly high for most LEDs these days. Where we lose energy is that the photons don't always make it out of the LED into our optical system. Okay, so what do we do with an LED? How do we use it? What do we have to worry about on it? Let's take a look at a data sheet for an LED. Okay, this particular data sheet that I'm looking at is for the WP710A 10ID LED. And I picked it just because it's a typical one. It's not the one we usually use in the class. It's one I happen to have sitting around. Okay, this one you can see is made not with silicon. LEDs are not often made with silicon. It's made with gallium arsenide phosphide on gallium phosphide. And it's the semiconductors that you use have to be picked to get the band gaps right, to get the particular wavelength that you want. If you used silicon as an LED, you'd get something in the infrared. And infrared emitters, in fact, do often use silicon. But to get visible light, you have to use other semiconductors. And gallium arsenide and various other 3-5 semiconductors. 3-5 refers to which columns of the periodic table of elements the elements come from. So they're column 3 and column 5, whereas silicon and carbon are in column 4. Okay, let's take a look at the package. We've got a package here and it labels one side as the cathode and one side as the anode. Which one is which? Well, the cathode is where the electrons leave the wire. That's true for any sort of electrode we're talking about. When we talk about an anode, it's where electrons go into the wire. When we talk about a cathode, it's where the electrons come out of the wire. So this side is the cathode, and this other side is the anode. And the current flow that we want to get the LED to light up is from the anode to the cathode. So the cathode is the negative end of the diode. All right. And as you can see on this particular LED, the distinction between the cathode and the anode is done by the length of the two wires, which once you soldered it into a circuit or something and trimmed the ends off, you're not going to be able to tell which one's the short one, which one's the long one anymore. A lot of LEDs also have a flat spot on the package to indicate either the cathode or the anode. You have to look on the data sheet to see what it means. This one doesn't seem to have a flat spot. Okay. Then there's some specs for the thing. This is saying that it's a high efficiency red, whatever that means. It's a red diffused package, so the package itself is red. It's not a clear package. And then it says how many millicandela of light we get, That's one of the many different ways that the brightness of the light can be reported. There's a viewing angle, and they're reporting the millicandela at 10 milliamps. So, in a sense, they're kind of suggesting that this thing is designed to be run at 10 milliamps. You may be able to run it higher current or lower current, but 10 milliamps is what it was designed around. In fact, if we look down a little bit further, we have got some electrical and optical characteristics. We've got two wavelengths, a peak wavelength and a dominant wavelength. Why are there two different wavelengths? This is sort of a weird thing about the way LED datasheets are written. Let's skip down a little further in the datasheet so I can explain this. We have got a plot here of the relative intensity of the light as a function of wavelength. And there is a peak here, right in the middle here, and it looks like at about 627 or thereabouts. That peak intensity is, or where that peak intensity occurs, is the peak wavelength. And so it's a physical property of the LED. All right, and if we look back here where it does that 627 nanometers is the peak wavelength. And notice they're giving this at a particular current, 20 milliamps. So I guess 20 milliamps is maybe really what they're designing this thing to use, because all their test conditions here were at 20 milliamps. So 627 is that peak wavelength. What is dominant wavelength? Well, dominant wavelength is not a property specifically of the LED, but a combination of the spectrum of the LED and the sensitivity of the human eye. Because your eye is not equally sensitive at all wavelengths. In fact, the wavelength which your eye is most sensitive is probably around 555 nanometers. That's in the green region somewhere. 627 is in the red. And you're going to be more sensitive on the greenish side of the red than on the infrared side of the red. And so there's a bit of a shift towards that 555 nanometers for what it looks like to your eye is the brightest wavelength. So the brightest wavelength for your eye is not the same thing as where there's the most energy coming out of the LED. So the peak wavelength is a physical property of the LED. The dominant wavelength is a combination of the spectrum and human eye sensitivity. Usually modeled human eye sensitivity, not actually measured for the human eye. And so you will see that the dominant wavelength is nearly always closer to 555 nanometers than the peak wavelength is. Okay, the next thing here, the spectral line half width, that's basically, I said that this thing was almost monochromatic. Well, it's not all that monochromatic. If we look down here at the relative intensity versus wavelength again, you can see it gets down to about half the intensity from between 600 and 650 nanometers. So this is a 50 nanometer wide band of light. And actually it says that it's 45 nanometers wide. So the plot and the spec here are not in perfect agreement. It's not clear which one is really the more accurate one. Okay, then there's some information about capacitance. This is, remember, a diode, when it's not conducting, is behaving like a capacitor. This is saying how big that capacitor is when you've got a 0 volt bias on the diode. The forward voltage, that's how much voltage you're putting on it in order to get the current to go through. And here they specify it at just a particular voltage, a particular current, 20 milliamps. So in order to get the 20 milliamps through here, you would need to have about 2 volts, maybe as much as 2.5 volts. The specification here is often fairly wide because the LEDs are not actually all that repeatable. In fact, you can pay extra to a lot of manufacturers for them to select particular bins to make this narrower. They don't actually manufacture them narrower, they test them and sort them into bins, and you can then buy, if you're willing to pay for the extra cost of the sorting, you can buy ones that have a narrower range of what the forward voltage will be for a particular current. And then there's a reverse current. That's if you hook the diode up backwards, how much current are you going to have just sort of leaking through? And they say no more than 10 microamps at reverse voltage of 5 volts. And then there's some absolute maximum ratings. Power dissipation. Don't dissipate more than 75 milliwatts, it'll get too hot. DC forward current, they say don't go over 30 milliamps. Go over 30 milliamps, you can burn this thing up. Notice that peak forward current is much higher, 160 milliamps. What's the difference between the maximum of 30 and the maximum of 160? Well, if you read the tiny little footnote here, that says that's a 1/10 duty cycle, 0.1 millisecond pulse width. If you only flash the light on for a very brief amount of time, 100 microseconds or less, and then you let it cool off for 9 times as long as you had it on, you can put a lot more current through this thing because you're not going to heat the thing up. The 30 milliamps is a continuous. If you have a continuous current of 30 milliamps through there, it's going to get too hot. If you do a pulse of 100 microseconds, you can go up to 160 milliamps as long as you give it enough time to cool down between pulses. Reverse voltages don't go over 5 volts. At 5 volts, remember, as they said that reverse voltage of 5 volts, you'd get 10 microamps through the thing. Don't go over the 5 volts reverse because, again, you can damage the part. And there's some stuff about operating storage temperatures and soldering temperatures and stuff like that. Okay, we already looked at this spectrum. And actually, I misread it. It looks like it is 45 nanometers, not 50 nanometers. It doesn't go through 600, it goes through 605. So the two specifications there were actually consistent. I just misread the plot when I was looking at it quickly. They give you a number of other things here, like the forward voltage, how much current you get for different voltages. And these are just typical, because remember there was a wide spec in what that forward voltage at 20 milliamps would be. They also show that the forward current and the brightness are nicely linearly rated going through 0. So 0 current gives you 0 light. 20 milliamps here claims twice what you get at 10 milliamps. They're just giving you relative values because, again, the specs weren't that tight on exactly how bright the LED is. There is a thermal deraiding curve which says, hey, if your thing's already too hot, then you can't put as much current through it because it heats up to the too high a temperature internally sooner. And it's basically saying, don't take this thing over 85 degrees C. At that temperature, the LED is no longer going to work. So they give you a deraiding curve for if it's between 25 degrees C, which is what they normally rate it at, and the 85 degrees C, how much current can you put through there? It's also showing that it gets less bright as it gets hotter. This is a standard property of LEDs. They get less efficient as they get hotter. And so generally you try and keep your LEDs from getting too hot. For what we're going to be doing, we're going to just be using low power LEDs. This isn't going to be a problem. But if you're doing lighting with LEDs, dissipating heat from the LEDs to keep them from getting too hot is a major concern. And then finally there's this plot of how bright is it in different directions. This package had a little lens at the end, and that focuses the LED into a fairly narrow beam, and that curve here shows you how narrow that beam is, basically how bright the luminosity is as a function of how far off angle you are from straight on. Okay, so that's about all I really wanted to show you about this data sheet, but I did want to show you one other plot, and that is measurements I made of one of these LEDs to look at the current versus forward voltage. And you can see it looks a lot like the plot they did. It's 0 until you get up to some voltage here, around 1.5 volts, and then it shoots up pretty fast. And people would say, well, there's a knee here, maybe around 1.6 volts, and it looks like it's two straight lines. A horizontal line at 0, and then a line going up sort of from 1.8 volts to 2.2 volts or whatever that is getting up to there. And this is an illusion. As you remember when I talked about looking at log plots, there isn't a knee there. There's nothing fancy happening at 1.6 or 1.7 volts. Let's take a look at this thing on a log Y scale. It's basically an exponential. It's an exponential up to about 1.7 or 1.8 volts, and then it kind of curves down and is not growing as fast. And this is why you have to be very careful in choosing scales on your plots. What is it that you really want to see here? If you're only interested in the currents from like 10 to 20 milliamps, in the range where we're normally going to be using LEDs like this, then this plot, which is giving all its attention to the very low current regions, isn't very interesting. And we want to go back to the linear scale, where 10, 20 milliamps is, a third of the plot. But if we were interested in the very low current region, the stuff that's down around 1 milliamp, this plot doesn't tell you much that's interesting there. And so you always have to choose your plots carefully to show what you need to show, to tell the story you need to tell about whatever it is you're plotting. In this case, they use the linear scale because you don't generally use LEDs at very, very low currents. They don't put out much light then, and that's usually not interesting in the application for an LED. Now later on, when we look at diodes for other purposes, we might care about what happens at very low light levels. But now, how do we design with the LED? We were warned that, hey, we couldn't put more than 30 milliamps into this thing, and we'd probably want to design around somewhere in the 10 to 20 milliamp range, because that seemed to be where they were giving the operating specifications. So what do we do? If we just put our 3.3 volt power supply across the diode, we're going to get some huge current. Notice that the top corner up here, the highest place I went on this thing, is 2.05 volts roughly and 21 milliamps. Well, that means that at 3.3 volts, if we keep going up this curve, it's going to be a huge current. Definitely too large for the LED. So what we do is we put a resistor in series with the LED. Okay, so, and we can put it on either side, it doesn't really matter. But for simplicity, I'm going to put it on top. All right, so if this is from the Teen CLC and it's 3.3 volts, we want to get something that limits the current here to, let's say, 20 milliamps. All right. If we want 20 milliamps through this diode, how do we get it? Well, I was just looking at that plot, and you could look at the one on the data sheet, and to get 20 milliamps, I needed about 2 volts across the LED. That leaves 1.3 volts across the resistor. So if I have 1.3 volts and I have 20 milliamps through that resistor, 1.3 volts over 20 milliamps is going to be, well, divide by 2 and I get 0.65, divide by 10 and I get 0.065, and that'd be kilo ohms, so that'd be 65 ohms. So if I wanted this thing to run about 20 milliamps, I would want a resistor of about 65 ohms here. That sort of resistor is known as a current limiting resistor. And we nearly always will have one with an LED. Now, if it turns out the LED has a slightly higher forward voltage for 20 milliamps, then what will happen is we'll get a little less than 20 milliamps through this thing, because if this is at 2.1 volts instead of 2 volts, then I'll have a little bit less voltage across the resistor and a little bit lower current. But the current limiting resistor works pretty well to do safe design for LEDs as long as you're not pushing the current limitation up to the maximum you can get for that LED. Okay, I think that's probably all you really need to know about LEDs for this course. You'll be using some in the pulse monitor, so have fun with them.